So right from the beginning, from the Big Bang all the way to now. So if we look, there is all this brightness in the beginning, but it's not until 400 million years later that we have stars. So the first stars are formed 400 million years later, and then we have all this progression through the history of the cosmos. How many of you saw the oldest star picture that was discovered last week? No one saw it? Okay. So this was a picture from the James Webb Telescope, and it saw the oldest star seen to date. It was reported on last week, the day before your workshop started here, your school. And it's the oldest and most distant star that's ever been seen. And it was just lucky that they could see this star because it's near galaxies with gravitational lensing, and it's like back there hidden, this star. This was seen by the Hubble a couple of years ago, and then the James Webb Telescope could get a better picture now. So why the James Webb Telescope sees this star? And why didn't we see it so much before? So if we look, this is the James Webb Telescope now. It has an infrared observatory. It's an infrared observatory. And that sees things into the past, all the way to this period, so the very oldest stars. So why infrared? That's just because it's redshifted. When things are moving away from us, the wavelength is shifted to the red. Okay, so this was pretty exciting discovery. It's the oldest star that has been seen so far. Perhaps we will see many more as time goes on. Okay, let's look at the history of the universe. Here's the Big Bang. Here's now. This is 13.8 billion years or so. So I look at the entire history of the universe in terms of nuclear physics. I'm a little biased. I'm a nuclear physicist. So what did we have at the Big Bang? We just had these very light primordial elements: hydrogen, helium, and lithium. And now we have all of these guys. This is what the elements that our world is made of. So how do we get from here to here? We can describe it in terms of some very simple figures. So we know the Big Bang, we just have the very lightest elements. And then some of the oldest stars, if they had enough time, they were making all the reactions with the very light nuclei. And we can get up to about iron or so there from the oldest stars. But there's no way to make all this other heavy elements in stars. So what is the focus areas of your work so far? Have you been focusing on stars or bigger systems, cosmological bodies? What have you been talking about so far? What's that? You've been talking about everything? Okay. Everything is a lot to talk about. So we will see. So it's basic nuclear physics that we know why stars make only up to about iron or so. This is mass number here. So this heavy mass like 56, iron will be around 56 right here. And this is all the way to 200. These are all the elements that we have seen. So what happens between here and here is astrophysics and nuclear physics. It's kind of wrapped together. If we could understand this structure, these abundances of the element, we would understand everything. If we know the nuclear physics, we could guess what situation in astrophysics caused it to happen. If we know the astrophysics, then we can guess what nuclear physics is at play. But its situation like this is that we have two unknowns. So how do we work with two unknowns? If you have some information about one, you can guess about the other. So this figure just shows, this is the binding energy per nucleon, and why we have stars that fuse elements up to about iron. So it's energetic. When we combine light elements, it releases energy. So that's the basis of all the shining of stars up to about iron or so. And after iron, down here, it's no longer, you cannot release energy by doing that. So you have to put in energy to do that next step. So that's why stars make up to about iron or so, cobalt, by fusing different atoms. And this other part, this is where you have fission, where nuclei fall apart and they release energy because the trajectory is in this direction where it's higher energy. So this basic figure explains everything in the cosmos. Okay, so when you're, have you been to Piragan yet? No? Are you going? Yeah. Yes. Okay. I have been there on when the electricity went out all over Armenia, and it was so amazing because you could see all these amazing stars. I even saw my first shooting star there. It was amazing. So typically when you're looking at the sky, you have all these millions, billions of stars. So all of them are at different stages of their life. Some are newly born, some are about to die, and everything in between. What's operating behind all those stars is nuclear physics. So nuclear physics determines how long a star is living, when it dies, and how much light it emits. So it's really everything from what you can see. So typically we have all this gas in space. You have stars forming out of the interstellar gas. And depending on the size of the star, that determines its history. So if it's a small star, it burns up the material, it joins, it releases light and energy, and then it becomes a red giant and could end up eventually like a white dwarf. And that's the topic of the speaker who's after me this afternoon. He talks about white dwarfs. Or if it's a very large star, it can become a red supergiant. It may even supernova. It may end up as a black hole or a neutron star. So all of this depends on what you started with. What do you have? And the factor, I apologize for putting you this definition from Wikipedia. Who looks at Wikipedia for stuff? There's a few people who look, I look there too. So it's the reaction rate or the likelihood of a reaction to take place is called the reaction rate. And that's what determines how quickly the star builds up and how much quickly it lives its life, how long it lasts, and how much energy it releases. So I put this definition here for us to use. And it can be very different for different stars. So this diagram is for what's called the main sequence of stars. What is shown here is temperature. This is in log-log scale. Temperature versus density. Am I talking too slowly for you? No? Too fast? Okay. So the main sequence stars are basically stars that are burning. So when you say hydrogen, so it's fusing hydrogen atoms. It can fuse helium atoms, can fuse carbon, neon. So the bigger the star, the more things it can fuse. And then when it runs out of fuel, it can also fall out of the main sequence. So we can have very predictable lives of stars. We can basically look at a star and see its size and what it's burning and know how long it's going to live. So observing stars, like 200 years ago, people thought, we'll never know what stars are made of. But that was before there was spectroscopy. Today, you can look at any star, look at the lines, and you know exactly what a star is made of. You don't need to wonder. And also, there are neutrinos coming from the sun. How many of you have heard of the solar neutrino problem? Okay, excellent. So what's that? So what do the neutrinos tell you? What do the neutrinos tell you?
Oh, I don't remember, but I memorized it. It's cool.
Vibrations in the solar form.
That's right. It tells you what's the signature of that star. So it's like measuring the neutrinos gives you the fingerprint of that star, basically. We come back to our chart. What are the first steps? So right after the Big Bang, the very first stars. I just showed you that the James Webb Telescope observed the oldest star we've ever seen. But we really don't have those first generation stars around. But you had to start there. The first stars, so they just coalesced from the interstellar gas. They were big. They were cool, not hot enough to make like carbon, nitrogen, and oxygen, not hot enough for that. So how are these early stars operating? And how were we getting from hydrogen, helium, and lithium to the elements that we know, even up to iron? How are we getting there? So we take a look at what we expected of the early stars, okay? So if we try to look what elements are being made from the Big Bang to now, basically, to a few 10 to the 14 minutes. This looks complicated, but it's not. So if you just follow me, it's about what are the abundances of the elements. This is log scale in seconds. So you start with hydrogen, which is protons and neutrons and deuterium. And then you end up at some time later with all these various elements. Okay? So the idea is you're starting with these hydrogen, helium, and lithium to make your stepping stones all the way to the heavier things. How are we doing that? So the first stars, this figure basically shows you, this is temperature and energy. So the energy is low in these first generation stars. There isn't the heat that's coming from all those nuclear reactions which set later. They're called CNO cycles. So the carbon, nitrogen, oxygen cycle is not yet happening. It's not hot enough to fuse those nuclei yet. But, so this is what's called a PP chain, and where is our sun in terms of that idea? So what about these first stars? They're mostly just made of the Big Bang primordial elements. That's it. They're very massive. 10 times, 100 times, maybe 1,000 times the size of our sun. What are the forces at play here? If it's so huge, what do you expect? I didn't hear. Pressure, so what is that? The pressure from what?
From the gas to the inside.
And what is that? You know it, so I just want you to say it. So it's gravitational pressure, right? And convection. I only say simple things, so if you think it's going to be more complicated, it's not. I'm sorry? What is here? What is PP? So in primordial, so you just have protons. So proton-proton fusion. I'm sorry? CNO is a carbon, nitrogen, oxygen cycle. Yes?
What is graph?
This is energy generation as a function of temperature. So if you are fusing alpha nuclei, making carbon, making nitrogen, making oxygen, you make a lot more energy. This is energy as a function of temperature, and it's hotter. But the first stars are not doing CNO cycle. They're cooler, and the energy generation is less. Okay? And so there's no CNO cycle to generate the heat and the energy, and they contract under gravitational force. So you were absolutely right. It collapses and there's pressure, but it's gravitational forces. So you can contract because it's all of this stuff is moving around, convection, and that convection ends in either a big explosion, like a core collapse, and you could have supernovae or you could have supermassive black holes. We don't think we're ever going to see a first generation star, but the signature has to be there. So how are we getting the elements that make life? Right? So the question is, how are we getting to carbon, nitrogen, and oxygen, and those signatures which are necessary in getting life? So a lot of this, there's different ways. You could do it different ways. The PP chain, so just combining protons, they're too slow to get to carbon. So they would fuse, they would fall apart, they would do all kinds of things, but you don't make carbon. So in a first generation star, you'd have to have higher temperatures, a deuteron cycle, and make the triple alpha. You could do it like this. So from nuclear physics point of view, these are hard to do. But nature does it. So how do you get from the primordial to the basic stepping stones that get you to the heavier things? So you could do it by, once you can make an alpha nucleus, you can then combine 3 alphas to make carbon-12. You can combine to beryllium. There's all kinds of different options. But here's the thing, if we don't make carbon, we don't have us. So carbon's important, and then if we don't make carbon, we also don't make oxygen. So I won't go into the details of how the energy profile works for all of these, but when we look at before the CNO cycle, we already have some signature of this element, even though we know they were not made in this fusion processes. So lots of pictures of reactions. So different reaction paths. You could combine different nuclei, but to some extent, even though not a lot, but you make a little bit of carbon-12, a little bit of oxygen, even though it's too cool to do that. Temperature-wise, too cool. So I'm an experimentalist, and I try to understand all of these things in terms of what experiments I can do. Now, if it's cool in a star, that means the energy is very low. So that means the energy in the lab is very low. We don't need the high energy accelerators. We need very low. And then, if it's very low, you have a lot of background. You have a lot of noise. We're always, like in Armenia, we're high altitude. We have amazing cosmic rays. We have a center that studies cosmic ray physics because we're high altitude and we get a lot of that. So where do you go? So the experiments go underground. This is the accelerator from my university, which is in a gold mine in the US, in the state of South Dakota. This was a very productive gold mine, but when it became more difficult to get gold out, the mine company gave it to the state as a gift, and the state turned it into an underground laboratory. This is 4,000 meters underground. It even has some places that's like 8,000 meters underground. So why go underground? No cosmic rays. The only issue you have then is the radioactivity of the rock that you're under. This is the accelerator at Notre Dame, some different setups. But basically, the idea is you want to have a quiet place where you can measure these reaction cross-sections without interference from background. I wanted to show you this, even though the details are not that important. I just want to show that we don't have, these are experimental points that have been measured for different reactions. So these are, the S factor is an energy-corrected reaction cross-section. But the point is that for the low energies, we don't have data. So you see, normally we're building bigger and bigger accelerators to get higher energies, but we actually here need lower and lower energy, but no background. Okay? So you see here, no data points. The red solid line is a fit. So because the energy is so low, you had to think about how else you could make carbon, nitrogen, and oxygen. I just want to present the idea that these are all the nuclear reactions that can place. So this is with neutron number versus proton number. So all these chains represent the reactions that are possible. So as a function of time, this is after 10 months, you can get a lot more reactions, and you actually make some carbon, and you make some nitrogen. Not very much, but you do. This is another plot that shows that the reaction cross-sections, this is a log scale, drop like this exponentially. It's so low. So you really have to be clever about how you measure that. And this is, you can get a picture of the sun from underground from the neutrinos that come there. So you can detect the neutrinos because they don't interact with anything. They go all the way through. And we can have a signature of the sun. The important point from these slides is just to show you that what's interesting, what is important to know, is where these arrows are, and we have no data there. Difficult to measure things that are very low in energy. So at the university that I'm from in the United States, we have 5 accelerators of different energies. And this is the lowest one, all different ways. So we try to go both underground and low energy. We took an accelerator to that gold mine and also the university. This is kind of the setup of the lab. This is one accelerator. This is another. This is another. So we have all different energies to explore, to measure the different reaction rates under different setups. So if we're trying to measure something that is so difficult to measure, so we're looking for something that's 10 to the minus 18. So you can imagine that if 1 is easy to measure, 10 to the minus 18, it's going to be really hard. So there's all different techniques for measuring this. And one technique is to build a recoil separator. We built this in the university so that when you make a nuclear reaction, you get most of it to go one way, but you try to measure that very low cross-section. There's other ways. This is the setup for Italy. Italy in the Gran Sasso Mountains has an underground laboratory. Some examples of how much radiation there is on the surface, this is in red, versus if you go underground, that's in black. So you reduce the background by that much. This was cosmic ray-induced gamma rays. This is underground, just the gamma spectra underground. You see there's orders of magnitude, 3 orders here, if you go underground. So going underground, or this is with 5 orders of magnitude for the neutron spectrum. So there's a lot of excitement to go. At the same time that physics is going to higher energies, there's also physics going to lower energies, lower backgrounds, in very quiet environments, so you can measure that. So this was the idea for us, to go with 2 accelerator system underground with almost 5 kilometers underground in this mine. This is how it started, the mine. Do you get to go to Avan mine, folks? There is a salt mine in the middle of Yerevan, and it's quite deep. So it looks more like this. It hasn't been built into a laboratory, even though we do experiments there in this laboratory. So this is the picture of how you go from top of the thing all the way down, and you can go even deeper. It's kind of a cool feeling, although strange. What's the first thing you might worry if you go underground? Pressure? There's plenty, there's oxygen, but it gets hotter. Temperature, exactly, it gets hotter. My biggest worry, I hate to tell you, was how do you go to the bathroom? I guess you didn't worry about it, right? And internet, but there is internet underground, and there are toilets specially made for being underground. But I was part of a team to select an underground mine for a laboratory in the United States. So I was going around to all these mines with these scientists to see which one is the best one. So I was a little nervous to start, like, how are we going to do this? Going down in these very deep mine shafts with all these guys stuffed in clothes. Okay, so different pictures of the mine before it was fixed, sort of like this. So putting in meshing and then cleaning it up to make it into a lab. That was intermediate. And then put the accelerator beamline in to do that. So today, who's doing these kinds of experiments? China has built a big underground facility in a mountain. were kind of unhappy because they stole our plan, but they built it faster than us in the United States. The Italians in the Gran Sasso Mountain. So the US is out of the game at the moment. There is an underground laboratory in Russia. I did the floor plan, but I have no progress of what's happening so far. Okay. So a normal star life. The star is born, it lives, it shines, depending on the size, then it explodes. I'm interested in what happens when stars die rather than when they're born. But so far we've come up to a star has lived and then exploded. So there's all different kinds of explosions that could happen. It could be because it was shock driven, like a core collapse supernova, or it could be that it was accretion driven. Accretion, so just collecting more material, and then it goes to a thermonuclear runaway. But are these environments the ones that are going to give us the heavy elements beyond iron? That's our goal. How do we get all these elements that you and I are made of? So if we look at, this is the chart of nuclides. So this is proton number against neutron number. So the black ones are all the stable nuclei. There's about 200 of them. And then these other colors on both sides of the black boxes are the radioactive nuclei. There's like 4,000 of them. And there can be more, but you have to make them in the laboratory. So you have to do different reactions and get very far away to the neutron-rich side or to the proton-rich side. Around the whole world, there's big efforts to try and study these different, to try and make these nuclei that are far away from stability. There's some physics there that we don't understand. We don't know when the nuclear force says, I don't want any more nucleons. I don't want any more neutrons. We don't know where that is. We kind of can guess where it might be, where it says, I don't want any more protons. So the nuclear force, as you know, we don't have the form of it. It depends on the numbers of neutrons and protons. It changes from nucleus to nucleus. It's not predictable like the Coulomb force that you can write exactly to 12 digits after the decimal point. There's a lot of effort worldwide to do this. So many places in Europe, many places in the US, Japan, China, everyone's trying to make those very heavy nuclei. Why? Well, we want to know, where did all the heavy elements come from? Where did the elements above iron come from? The most popular two scenarios were like supernovae or neutron star mergers. Why am I saying or? Can it be both? Well, observers, astronomers, had measured lots of different stars in different galaxies, and they find that the abundances are very much similar no matter what star you look at. So this kind of points the finger to saying it has to be the same process wherever it is. Neutron star mergers, until one was observed, people didn't think that it happened frequently enough to make all the elements we have in the universe. Core collapse supernovae, all the simulations of core collapse supernovae showed that you ran out of neutrons before you made all the heavy stuff. So it was a bit of a problem. Where are you making those heavy elements? This was one of the biggest challenges for all of physics in this century which is 22 years old now, right? So we came to the 21st century and we still didn't know where the heavy elements were made. We know the nuclear physics, we knew what had to have happened for the elements to be made. We didn't know where those conditions were that could make them. Where were those conditions? Both of them didn't seem likely. Neutron-star mergers seem like unlikely, it's very rare. And the core collapse supernovae ran out of neutrons when we know that we have uranium and actinium and plutonium. So how did we make those? And this simulation here shows you the process. So we knew that it had to be neutron capture. We knew it had to be fast neutron capture. If it just neutron capture slowly, it would decay back. So it had to be successive neutron capture very quickly for it to go very far away. So this is now stability, and you see what happens to the reaction, and then it builds the abundances you see here on the inside. So there's a lot of nuclear physics involved in all these reactions. I'm not going to torture you with it, but before we observed the gravitational waves 5 years ago, we were trying to do everything we could to try to figure this out. How does it work? We were trying to use nuclear physics to guess what the astrophysics was. Okay. So no need to pay any attention to the details. So a lot of my work was trying to use nuclear physics to determine what astrophysics conditions we had to have to make the heavy elements. So we were making experiments, we were doing calculations, we were trying to say what kind of an astrophysics scenario would make these nuclei. We know nuclear physics works a certain way. We know the mechanism. Anyways, I'm going to go through very fast here. Actually, this picture, with just in pink colored areas with this black line, this was motivation for the US to spend $1 billion to build a facility so that we could measure some of these nuclei that are so far away from stability. So they did that. This facility just started to operate this year, a couple of months ago. Lots of pictures. All of it was based on trying to guess. Was it neutron-star mergers that made the heavy elements? Was it supernovae that made the heavy elements? Was it something different like that, something in between? So it was all a lot of measurements to try and get there. Lots of new techniques, some old techniques to try and do fission. So this is fission distribution plots. So we said, how can we make these nuclei in the lab so that we can prove that what we're saying is that it happened in a certain scenario? Lots of experimental effort to do all of these things, lots of techniques. So developing penning traps to measure a nuclear mass to a few electron volts. This was a huge innovation and changed all the applications of nuclear physics. I'm just going to rush through all of this to try and say, okay, so we think this had to be this region. What could we do to get to this region in the laboratory with accelerators? And then what could we do to measure it precisely so that we eliminate any uncertainty from the nuclear physics? And we could clearly say this was what happened for the astrophysics condition. Okay. Too much detail. We'll go ahead. We suspected lots of things. This figure is just to show you all the different places around the world that are involved in trying to make these measurements. So Finland, Canada, Germany, CERN in Europe, This is the US, Germany again, GSI, Oak Ridge, lots of places. A lot of big effort experimentally all around the world. And then came 2017, August, and there were gravitational waves detected from 2 neutron stars that collided into each other. So first it was just the physicists that were really excited, but very soon it was the whole world was excited. Why? Because immediately people realized, oh yeah, neutron star mergers, maybe it makes gold. Of course, it makes everything heavier than iron. The people started to pay attention because it was mentioned gold. It makes gold. So every newspaper, every country around the world was saying, okay, we found how the universe makes gold. This is from Science magazine. They said, okay, neutron star mergers may create much of the universe's gold. This is an English newspaper saying, secret of gold finally found. Precious metals are forged in cataclysmic collisions of neutron stars. So when there's money involved, everybody was paying attention, right? This is a German business magazine saying astronomers detected 100 Earths worth of gold being forged in space. Here is how much it's worth. So they calculated it. The Germans tend to do very precise things like that. It says the gold alone, forged alone, is worth $100 octillion. There's $100 octillion. So I got lots of calls from TV stations and newspapers saying, so, you figured out how to make gold. So even this magazine, Financial Times, started to talk about how can you mine this gold? How could you go to space and mine other things? I mean, you see it in the movies, right? People are talking about mining different planets or traveling to different galaxies to get different things. But in science fiction movies, I mentioned the fact that this century, there were 11 questions that were considered to be the most important questions we don't know the answers to. And this, where were the elements from iron to uranium made, was one of those 11 questions. In the whole history of the universe, did we figure it out? Is this it? Neutron star mergers, do they make the heavy elements? Some of you agree that this is probably where they make the heavy elements. But what evidence do we have? Well, nobody collected any gold. Well, the neutron star merger happened 132 million years ago, and the signals just arrived on Earth 5 years ago. But this figure explains it all. So the minute the gravitational waves were observed, people turned all their satellites flying in space. There were 70 electromagnetic satellites that turned to look at the origin of the gravitational waves. And there was a lot of data. Since then, there have been gravitational waves observed from neutron star mergers, but we don't have as much information as we did from this one 5 years ago. What did they see? Visible light. They saw all the elements being made. So the lighter elements were making in the blue, and then they get into the red. Does anyone know where the color is coming from? Yes, the spectra, but because of the atomic levels, right? So the lighter elements have further spaced energy levels, and those transitions are in the blue wavelength. And then when you get to the heavier elements that have really tight atomic orbitals, you start to get to the red. But here's the story. You only saw visible light up to lutetium. Does anybody know where lutetium is? So lutetium is here. So you didn't see that it made gold. We didn't see that it made gold. We didn't see that it made uranium or any of those other things. Because the light that's emitted, the atomic orbitals became so dense, by the time you get to lutetium, which is in the rare earths, that it went into the infrared. Now, if the James Webb Telescope had been up, you would have had lots of extra information, but it wasn't up. It was delayed, so it was not up. So visible light, we could only verify that things got made up to about lutetium. So the question that comes up is, did it go all the way to make the heavier stuff? We don't know. So I wrote an article just the end of last year for Nuclear Physics News International, and I said, now this opens a whole new question for nuclear physics. Because if it went beyond lutetium, and we don't see it in the visible light, it would have to get all the way to the actinide region, so like uranium, plutonium, and that region, and it would have to fission back. But it raised a question of, does fission change when you have a neutron star merger? Is it a different kind of fission than normal fission? We don't know. In nuclear physics, we've been studying fission for 80 years, but we don't know what happens to fission when you have a lot of neutrons. So this is normal fission. If you have an isotope of uranium, it splits into two, depending on what kind of things you do. But if you had a lot of neutrons, it splits into three peaks. And sometimes it does all of this. These are all theory, though. We have no experimental evidence that this is what happens. But if it does, and I think it does, then we can search for a lighter component of this, and I can tell the astronomers, go look for this. It should be in the visible light signature. So that's my idea. I'm still working on it. I don't know if I'm going to solve it, but I'm not the only one working on this. You know that this last set of elements were all filled in from work at Dubna. So this is moscovium, flerovium. This was all work inspired by Flerov at Dubna. And Oganesyan, as you know, Oganesyan is the only living person who has an element named after him, Oganesyan, 118. And everything in between, you see livermorium, tennessine. These projects, this last set of elements were made in the laboratory, and it involved collaboration of the entire world. So it involved collaboration of Americans, Japanese, and the Russians. And everyone that collaborated with them. So this question of what happens to fission is something that's being explored at Dubna. You probably may have heard about it. It's a place called Super Heavy Element Factory to make these very heavy elements. The facility is amazing and did 1,000 times more statistics than anything else. But then there was COVID and had to be shut down because people couldn't run to answer the questions that were to be answered. But what about these heavy elements? We put it in our periodic table of elements, but do they behave as we expected them to? So you see, oganesson is supposed to be a noble gas. Is it? When you make it in the laboratory, you have only a few atoms. How do you judge if it's a gas or a metal or something else? It's supposed to be a gas. But when you do the relativistic corrections from chemistry, you find that it's actually not a gas. It looks like it's probably a metal, but we have to make enough to test that idea. We don't have enough in the laboratory. You make a few atoms, yes? I'm sorry? No. A gas and a metal?
I mean, maybe.
Do you mean if you excite it or something like that?
No. They have properties of gas and metal.
I don't think so, but perhaps something new will happen that could change my mind. I don't think so, because the chemistry of the element has to be determined completely by the number of electrons. And when you have so many in this last row, that there are relativistic effects that were not calculated when you had the other elements. But still, we have to wait.
What if the problem is in classification?
The problem is what?
In the classification way we describe the elements, any of the last ones.
Yeah, exactly. So that's all I had to say. I wanted us to sort of have an idea of what the challenges are, what questions we know the answers to, and lots of questions we don't know the answers to. And I hope that someone in this room or someone's in this room will be able to help with answering some of these questions later on. So thank you for your attention. I'm happy to take questions.
Okay, we are to see the big mountain and the low mountain. Why is there a low mountain in this?
Yes, figure.
Why there's a low mountain in this graphic?
Why is the low mountain what?
In this graphic, you can see.
Are you asking why there is a peak here? Why is not continuous?
Yes, why is 2 peaks not 1?
Yes. Okay, so this has to do with the closed shells and electrons, because you're making the elements as you go along. So just the same as you do with nuclei. So the question of why is there a peak here? So some of it came at different angles, like came off from the kilonova, ejecta, and came later. Why is the color different? We know. But why is there a peak? So you make a lot less of this heavier element. And that's kind of both physics and chemistry. Because if you look at the abundances, like if I go, so this is a mass fraction in log scale. So if you look, these are all the elements from the very light to the heavy, and you see you have peaks here. And this is because of the nuclear physics. So you have closed shells in nuclei, just like you do with atoms. You make a lot less of them. A lot less. This is orders of magnitude less.
Why there's a lot of elements of red peak?
Why is there so many of
Yes,
red peak?
Drivers came slower, but when they have a heavy peak of heavy elements.
Yeah, that peak of the red is when you're making all those middle elements, the rare earths, and that corresponds exactly to the abundances of the elements in the universe. Like if you look at the abundances of the elements in the periodic table and you plot it like that, it would come like that. What's that? Can I explain in one more simple? Okay, sure. Let's see. So, like the periodic table doesn't tell us what element is more abundant than other things, right? So we know these are noble gases, but we know in the universe there's a lot more hydrogen and helium than all the others. We know there's very little like uranium and plutonium and things like that. But we really need to look at, this process is just run away like this. This doesn't give you any intensity. But if you look here, you see in the beginning you have this big peak and you're making stuff and then it decays back. So basically what you're ending up with, like if you look at the nuclear physics part, this is just an example here. You have in that region of 140, 150, that's where that's where the red peak is, here. But we cannot detect the peaks from here forward. We couldn't detect it because it was in the infrared.
So there can be more peaks?
Yes.
Oh.
There can be more peaks later on, but now if there's another 2-neutron star merger, James Webb telescope will be able to see the peaks all the way down. Yes?
I have a question about one of the first slides. There is a slide with a mass fraction, and can you turn one of the first slides? It's the second slide on the third level.
Yeah. Mass fraction is proportional to the intensity. The abundance of that element, not intensity, abundance.
This one, yes.
Yeah.
So about.
So this is related to abundance. Here.
So there is about zone stars, but why is that heavier than Hero there? Like it's something that is more less number than
It's this point that you're talking about, right? So, like our star, the sun, has been through several supernovae. So it has heavy elements, even though the sun is not hot enough to make those heavy elements. So you have this combination of stuff which has come from former lives, basically. It should, in terms of energy, you basically run out around cobalt and iron, you run out here. And the extra stability of those elements is what is the variation in this peak here. So it's the binding energy as a function of nucleon. There are certain nuclei which are very stable, like helium-4, alpha particles. So you combine then 4 alpha particles and make oxygen, or 3 and make carbon. So those are very stable. Stable in terms of it takes a lot of energy to break it apart. So. Mm-hmm.
And there was something about beryllium 8. That in the early universe there was amount of beryllium 8 in addition to the hydrogen and the helium and the question is if there was the beryllium in the universe.
Yeah.
It could be in stars, so where is it?
Yeah, it's. We don't know that there's any beryllium. You see, there's no beryllium 8 here. And the lithium, so the whole discussion is, what happens, how come we're not seeing as much lithium as we should see? and 1,000 times, up to 1,000 times of the predicted lithium-6 is observed in stars. So there should be a lot more lithium-6. This is the lithium-6 mass fraction compared to lithium-7, and then the beryllium-7. So this is a problem.
But what's with beryllium in stars?
It's not there. I mean, why is the number 5 and number 8? You see here, there's no helium-5, and there's no beryllium-8. And this determines the life of a star very well. So you see that we have helium-6, but helium-5 is not stable.
So it was in early period, but because it's not stable.
It just decays back, yeah. Just not there. I mean, it doesn't stay, so.
But there was.
It wasn't there to be observed because every time you make it, it falls back apart. It doesn't stay. It gives no abundance. Okay, so all these reactions are possible all the time, but because of the nuclear physics, some of them just decay back. So there's no mass 5, there's no mass 8 here. Yes?
Yeah, isn't it dangerous to put a lot into
No. Dangerous how? So if you have like electrical failure?
No, like for example, if the mine falls or something like that.
Oh, in those pictures, did you see there was a metal mash and then the fendits? So the rooms in which the accelerators are secured, so they're solid. But in any mine, if there is some collapse somewhere else in an unsecured area, that could be unsafe. The other danger is if there's fire, then the smoke, there are escape routes of where you could go and breathe in every mine. You know, the stories with miners always carried a canary, and if the canary died, they knew to get out of there for the poison gas. Yeah. It has its dangers, like everywhere else. But you have to have the right conditions. So breathing air and temperature is the most important stuff. Yes?
I have 2 questions. How does that decide which mine is the best, which will become used as scientists later?
Yeah, that's an excellent question. So we looked at a number of mines across both Canada and the United States. So what you want for the mine is to be stable. And if it's a working mine, you want to be sure that you have access to do experiments all the time. So there was a very nice mine, but it was being used for mining of, I think, copper. And they didn't want to allow experimentalists to enter all the time. The other thing is radioactivity. So different rocks have different levels of radioactivity underground, and if you want to have a quiet environment, you want to pick a mine that has less radioactivity underground than something else. Salt is fantastic, but salt flows. So if you make an accelerator in a salt mine, and there is such a place in Romania actually, the accelerator can shift because the salt is actually flowing. It's not, it looks solid to us, but it's flowing.
In this Can you tell us more about the oldest star?
The what stuff?
Can you tell us more about the oldest star?
The old stars?
The oldest.
The oldest stars. Okay. Yes. Unfortunately, I don't have enough pictures. I could show you abundances. Let's see here if I have some pictures at the end. The question is, how do you get to, if we look at the very oldest signatures, like you had to have some way to make enough carbon, nitrogen, and oxygen. So we're saying in these oldest stars, it's not enough hot to do the fusion reactions like we thought, and the proton capture ones are too slow. So there are signatures that there had to have been some made by the other mechanisms. That's what I had tried to show, was that there had to be a different approach to making some signatures of carbon and nitrogen before it's hot enough. And the process there is because of the convection and the pressure, so the collapse. So you do make some carbon, nitrogen, and oxygen, but not as much as you would later on when the star is hotter. Just because we don't know how to explain all the beginning. So that's why I call it stepping stones. So you start someplace, you step to the next, and step to the next.
Yes, so I have a question on the next slide with elements fusion. Yes. There is the, let's say, wall, as you said, that this is the edge where elements first the fusion, then the fission, and the edge is the ferrum. It's iron.
This here, you mean?
Yes, yes. It's ferrum, as far as I understood.
It's close. It's iron, cobalt. It's this region.
Yes, and I'd like to ask you, why is that so? What's the reason for it?
If we add up the masses, so it has to do with, this is binding energy per nucleon. So when I start to put in nucleons and then look at the entire mass, so it has to do with the nuclear force. So if I have an iron 56, it's what, 28 neutrons, 28 protons. If I add up all the individual masses of 28 protons, 28 neutrons, the mass of iron 56 is much lower than it would be just because I added up all those protons and neutrons. And when we go lighter than that, so here, like if you combine hydrogen to hydrogen, so basically, let's say helium-4, you release 28 MeV of energy per binding to make a helium-4. But over here, you cannot add another neutron. So with fissioning of this nucleus pushes it this way. So you basically end up something that's mass 90 and mass 145. So both of those are higher binding energy than this per nucleon. So that's where the energy comes from. It's a mass difference. It's just E equals mc squared. When you put it on a scale, the lighter nuclei are more tightly bound.
And the other question is there any relation between this fact that you just explained and the magnetic, things that are related with iron?
I don't know it. So I don't know if, I haven't thought about that. It's an excellent question. I don't know.
Thank you.
Yes.
Is it possible to predict that supernova will become black hole or something like that?
It's mass dependent. That's right. You can do. And I was working with some colleagues that actually could predict a supernova before it happens from the neutrino signatures. Unfortunately, I don't have that picture here, but there is some signature that you're about to have a supernova. So you do know what's going to happen depending on the size.
Theoretically, can James Webb measure the elements from 108 to 108 speeds, and if he will see it, what will it mean for astrophysics?
Excellent question. You see, you asked me the question about why is the peak of the light, so you have two peaks. Why is it not one continuous peak? So in that peak is every single atom from beginning to, let's say, mass 160. So an atomic excitation of a given element give you thousands of lines. So you have to separate those, and you have to know those very well. So yes, James Webb can measure it, but then you still have to identify where it's coming from, which element it's coming from. What I'm trying to do is kind of easy way to find the lighter partner of a fission thing, but still I have to go to astronomers and I have to say this element has, everyone knows what the atomic signature is of a given element, and they have to look for it in all that complicated and continuous data. Of course, atomic transitions are discrete. They're fixed energies, like a fingerprint of a person, but they are all together complicated like that. You have to disentangle it all. So yes, James Webb telescope can see it. It won't be a straightforward process. It will take some analysis.
What is the oldest star in your first picture, in the first slide? Is it white dwarf? Is it white dwarf? What is this? Yes.
It's still a living star. Well, the signal is coming to us from the time that star may no longer be there, but it was created when the universe was 7% of its present age. So now it's 13.8 billion years old. So let's say 10 would be 1.38 billion years old. I'm sorry?
Is it a simple star or white dwarf?
No, it's a star. I don't think any stars are simple, but yes, it's a star. Or was a star. It was only enabled because there is something called gravitational lensing, because you could see the light because of the galaxies nearby that made it possible. Otherwise, it's way too weak to have been detected. And the name is Earendel. The one before this, that was the oldest, was called Icarus, thinking that was the oldest. But that was 3 years ago. And this is now the newest, and it was just a week ago.